In a previous video, we've looked at derivatives of complex functions. So if we have a derivative f prime of z evaluated at a certain point z, we wanted to have the situation where the result was independent of the direction of approach. So you get the same result regardless of how you approach the point z. And in a previous video, we've shown that if this is true, then it means that the famous Cauchy-Riemann conditions hold. Now what we're going to do in this video is see if we can flip the direction of the arrow here. Let's say that if the Cauchy-Riemann conditions hold, can we then also show that the derivative is well defined, independent of direction of approach? In other words, can we also show that the Cauchy-Riemann conditions are not only necessary, that's this direction, but are they also sufficient, that's that direction? Okay, that's our goal for today. In order to do that, let's do some symbolic manipulations of differentials and derivatives here. Let's start out by writing what df actually is. Since df depends on both x and y, we can trivially write this as partial derivative of f with respect to x dx plus and then something similar for y, df dy. Okay, we also know that f consists of a real and an imaginary part. So now we can write this as du dx plus j dv dx. Okay, and then something similar for our second term when we take the partial derivative with respect to y. So f is u plus jv, so we have du dy plus j dv dy. We're not really interested in df by itself, we're interested in the ratio df dz when we want to calculate the derivative. So this means that if I just copy and paste the numerator here, so du dx plus j dv dx, and then plus du dy plus j dv dy, and then we divide by dz. And dz obviously consists of a real part and an imaginary part as well. So this is going to be dx plus j dy. I'm going to do a final manipulation here, and that is divide everything by dx. So both the numerator and the denominator, I'm going to divide them by dx. And that gives us, if I copy and paste one more time, hopefully not making too many errors in the process. So here the x cancels because we divide by the x, and then we have du dy plus j dv dy, and then here we have dy over dx, and then for the denominator, if we divide everything by dx, I'm getting 1 plus j and then dy over dx. So far, the only thing we've done is some symbolic manipulation of this derivative here expressed as differentials. The question is, how does this help us? Remember our goal? Our goal is to show that the derivative, so this expression, does not depend on the direction of approach. So pause the video here and try and think about where the direction of approach is encoded in this formula, and then see if you can use our friends Cauchy and Riemann to get rid of that direction of approach. So pause the video here and see if you can figure out the correct answer. So where is the direction of approach encoded? So if we have a simple example here, x, y, and then a point z, if we approach in this direction, that means that dx is equal to 0. And if we then calculate dy over dx, because we have a suspicion that that encodes the direction of approach, yeah, that's basically infinity if you want. In this direction, dy will be equal to 0. So here, dy over dx will be equal to 0. If we approach along the diagonal, then dy will be equal to dx. So in that case, the ratio dy over dx is 1. In any case, the important message here is that it's indeed dy over dx that encodes the direction of approach. So a different value of dy over dx corresponds to a different angle here. So our ultimate goal of today is getting rid of this dy over dx, which we find here in the numerator and also there in the denominator. So how do we achieve this? We still have our secret weapon, which are the Cauchy-Riemann conditions. And let's use the Cauchy-Riemann conditions to transform this particular expression over here. What we're going to do is have a look at du dy plus j dv dy. If you look at the Cauchy-Riemann conditions, you will find that du dy is minus dv dx, okay? And then dv dy is du dx. So here we have plus j du dx. Let's now rewrite this a little bit nicer by factoring out a j and bringing the derivative with respect to x as the first term. Then here we have then plus j dv dx. Does this work? Well, indeed, we have j times j, that's the -1 we also find here. Good. So now, if I can bring back our equation over here, what we're going to do is take this term here and substitute that by that term over there. So let's do that. We can write that our derivative, df over dz. So the first term I just copy and paste from what we had. So if I go back, so that's du dx plus j dv dx over here. So du dx plus j dv dx. And then for the second term, that's this guy going to be replaced by that expression over here times dy dx. So now we have plus j du dx plus j dv dx. And then we have that nasty term dy over dx that we want to get rid of. Okay. And then we still had a boring denominator over here, which we're just going to copy again. So this is going to be 1 plus j dy dx. And now the fun part begins, because this thing here and that thing here are the same, so we can factor them out. So this means that we can write this as du dx plus j dv dx. And then we have in numerator 1 plus j dy over dx. And in the denominator, lo and behold, we also have 1 plus j dy over dx. And that is indeed what we were after, because now this thing cancels. And we can write that df dz can also be written in this particular form. So only taking the partial derivatives with respect to x of u plus jv. So we've gotten rid of the direction of approach. We've also shown that the Cauchy-Riemann equations are not only necessary, they're also sufficient.